Good afternoon, everyone. We are recording, and let's start. Okay. Good afternoon. So we are on lecture 9 today. And today we are going to start off talking about a slightly different form of regression. So let's see. So we've kind of built up the trajectory of the course, starting with linear regression, talking about metrics with which to evaluate the model, right? And then we introduced this concept about bias and variance, and we're talking about increasing or decreasing complexity of the model. And two of the ways that we've looked at that so far are with subset selection, right, with stepwise regression, and then with regularization with lasso and ridge. So we're actually going to step back now and think about a different form of regression. So going back to, as we're building up from the linear regression, adding more variables, and then also thinking about adding dummy and categorical variables. And so those have primarily been on the explanatory variable. So our y's, or our response variables, have always been continuous, right? But there's a question of, can we do these types of regressions where your output or your response variable is actually a dummy variable or a categorical variable? And so the simplest form of this is known as a logistic regression. Okay, and so this is a regression model where the response variable is categorical. So discrete rather than continuous. Okay. So the simplest example, kind of in the same vein as we talked about dummy variables being a subset of categorical variables. So simple example is for binary outcomes. But this will extend to multiple outcomes. And we call that form multinomial logistic. Which we'll talk about later today. So logistic regression, we're starting here because this is kind of the simplest method that folks have devised to be able to run a regression on a categorical variable. But more generally, it's not the only way to do it. Just like a linear regression isn't the only way to run a regression on continuous data. When an outcome is categorical, this is also referred to as a classification problem. I guess that's lingo that's common in the machine learning world. We call discrete regressions classification. Yeah, so if you hear classification, it just means that your explanatory variable is categorical. Okay, and so really we think about something like some input going into our model, and you might have like a yes or no outcome, right? And so, in, let's say, the transportation field that I work in, right, you might have a question of like, do I want to buy a car? And you have income, you might have something like education, and so here you might have continuous variables informing that, but you could also have discrete variables. So something like this, and then, yes or no. Okay, so let's first start off. Why have a different sort of regression form for this type of problem? Why not just run a linear regression? Okay, so if I have y equals, let's say, beta 0 plus beta 1x, right, we would have something that looks like this, x, y, and maybe we would have some regression line like this. And so let me make that a little bit shorter, actually. So here. What is the problem with this in the context of what we're talking about here? Like y being a categorical variable. Yes?
You can't really have a slope. Your output would be stepwise. So just sort of suddenly be at another value discontinuous.
Yeah, so what are the allowable outputs? Or what are the allowable values of y?
0 and 1.
0 and 1, right? And so we have here 0, and let's say 1 is over here, right? But then your model fit can be any of these values, right? Yeah, and so one thing that I'll say is that with outcomes of 0 and 1, there is something kind of interesting and functionally related to outcomes in regressions, which is that any regression model that you run, for any result that you get from that model, is it like a definite result? I see you shaking your head. Yeah, you wanna expand a little bit? Am I being too vague? So there's uncertainty, right, with your results, and so in statistics we're usually talking about probabilistic outcomes, right? And so when it comes to zeros and ones as outcomes, one thing that folks kind of gravitate towards isn't necessarily just a prediction of zeros and ones, but to actually think about the probabilities associated with the outcomes, right? And so rather than this y value here, maybe instead I'll use p of x, which is the probability associated with a particular outcome. Okay, and so let's get rid of this guy, and instead I'm going to write p of x here. And so if I'm talking about probabilities of outcomes, the way that people often treat this is like if you're below 50%, right, then you might be with the 0 outcome, and if you're above 50%, you might be with the 1 outcome. And so we'll see a better example of this that hopefully will be more concrete in just a second. But now that I am operating in probability space as opposed to just zeros and ones, Now, what do we think about this particular line?
Doesn't seem possible.
And why not?
It's continuous.
But probabilities are continuous, so that can't be the only reason, right? What do you guys think? So, where are probabilities bounded? Yeah. So probabilities have to be bounded between 0 and 1. And so by thinking about this in a probability space, I've actually solved one issue, which is that my outcome can now exist on a continuous scale, but I have a problem, which is that it extends past 0 and it extends past 1. So we have to have some way of dealing with this. So to keep ourselves in a linear framework, there's one thing that we could do, which is to actually transform the data, right? So this is very much akin to doing like a log transformation, right? The purpose of doing a log transformation for data that looks exponential is to linearize it so that we can keep using a sort of linear form of regression. And so there's a similar concept here in which I'm going to try and transform now my my response variable and see what happens. Okay, so if we call this 1, what about if I do something like this? P of x over 1 minus P of x. Does this look like anything to anyone? What is probability of an outcome divided by 1 minus the probability of an outcome? Does anyone place any sports bets? Yeah, so this is an odds. Okay, so if you ever heard of like a betting odds or something, it is in reference to probabilities that are arranged in this way. So if we do something like this, and you were to graph this, P of x over 1 minus P of x. So this is unbounded probabilities here. And then this is going to be something like this. And this is unbounded in one direction. So 0 to infinity. This actually looks like a, well, actually, let me get to that in a second. So in this case, we're getting a little bit closer, and you still have an issue that you are unbounded in one direction. But you are limited in the other. And one issue is that this particular form isn't a good representation of your probabilities yet because you are unbounded in one direction. You're still going from 0 out into infinity.
For x or probability?
For your probability, right? So remember, our probabilities we want to be between 0 and 1. We've done this transformation to turn it into this odds ratio. But in the odds ratio, we've successfully bounded the bottom to be bigger than 0, but the top end is still infinity, so you still can exceed values of 1, right?
So is odds like, what's the difference between probability and odds?
Well, the relationship between a probability and an odds is something like this. So let's say the probability that I don't know who's in the playoffs right now. The Lakers go to the next to the semifinals is going to be let's say it's 20%. Okay, so that's the probability. The odds would then be 20% divided by 1 minus 20%. So it'd be 0.2 divided by 0.8. So 0.2 over 0.8 is 0.25. Yes, right. So the odds is 0.25.
So you've gone from describing it as a percentage to describing it as in like terms of 1 in X chance. Yes, because that's 1 in 4 or 1 in 5.
Is that? I don't think that's quite how you describe an odds, because they have. Oh well. There's in odds with 0.25. I think the way you think about it is there's. Actually, I've never actually tried to think about odds that way. What is the?
I'm just trying to understand like what if I see in odds a number that represents odds, how do I interpret that? Just like a ratio.
Yeah. Wait. So okay. So help me out here. So
If you're looking at like a sports book, it'll be like 1.41 or something.
it's like 1:4,
Yeah,
right?
Whatever,
Yeah. So then.
I think that's saying for every 4 events on the right side.
No. For every 1 in 4 would be 1:4 would describe there's 5 in 5 repeated occurrences. 1 time you'll have that one outcome. 4 times you'll have the other outcome. That's how the odds works. Yeah, a little bit counterintuitive. Well, I don't want to say counterintuitive, but the way we think about these, actually, I'm gonna go back to this in a little bit when we think about the interpretation of the betas, which are in by default this transformed term, which I think actually makes it a little bit confusing. And yeah, I'll have some suggestions about how to kind of deal with that, because I don't like dealing in odds and in log odds, which is actually the next thing that I'm going to talk about. So log p of x over 1 minus p of x is equal to beta 0 plus beta 1 x. Oh, sorry, this is this. Okay, and if I plot this, p of x, then you actually get something that looks like this. Oh, wrong color. You get a sigmoidal curve. And now you are bounded between 0 and 1. Okay? And importantly, this regression becomes possible because if I were to plot x versus log p of x over 1 minus p of x, which is known as the log odds, then you get a straight line. And so that the form of that equation is linear in parameters, which is what you want to be able to do for right these forms of regressions. Yeah, so don't ask me to interpret log odds because I have no idea how to interpret that. Log odds are a lot more confusing. It is a construct with which we can essentially get this outcome that we're interested in, right? Which is to bound our outcome to be between 0 and 1. Okay? All right, any questions about this so far? All right, so let's jump over to R and see how we can implement this. Oh shoot, I was supposed to. All right, I'm gonna quickly upload a data set into Canvas. So give me one quick second so that folks can follow along. Sorry, I forgot to do this before. Two-factor. Okay, this is kind of a silly little example, but I'm going to upload a data set called elections. In just a second. Yeah, so you should see something called election parsed. Okay. Election data, read CSV, election parsed. So this is a really simple example. It is data by counties in the US, and basically they were looking at different elections, and the first column indicates whether a Democrat won or not, and the second column is the percentage of registered Democrats in the population of that county, right? So technically you could have more than 50% registered Democrats, but you could still lose an election, right, if they chose to vote a different way, or they chose not to vote, or whatnot, right? And so, but generally we would expect, right, the higher percentage of registered Democrats in a county, the more likely that a Democrat wins in that election. So let's take a look at this. And we're going to run a new function called GLM, which is a generalized linear model. And we want to look at the outcome, which is whether or not a Democrat won, regressed on the percentage of registered Democrats in that area. We're going to use election data. And here, importantly, you have to specify the sort of functional form of the output, which is binomial. So we're just going to run a simple logistic regression. And we can run it like so. All right, so we can run a summary of the model. And we've got a couple of new things to look at here. Okay, just like before, when we look at a summary, it tells us our formula. We have some residual information here, and then we have our coefficients with our standard errors. Okay, well, with this stuff, I can say, well, they're both of the variables are statistically significant, referring to the intercept and percentage Democrat. All right, so who wants to interpret this for me? Anyone?
They're probably not zero.
Yeah, they're probably not zero, but specifically, what do these values represent? Yes.
Well, I would say that with a higher percentage of registered Democrats, the likelihood of Democrats winning increases. That's why percent Dem is positive, I would say.
Okay. Yep. So if this is positive, it's more likely that the outcome is in the whatever the one is, which in this case we've coded to be that the Democrats win.
Yeah.
And then if this is negative, then
I guess the zero is very unlikely, but I don't know what negative means.
yeah. Yeah, so what do these values mean? Yes.
Do these coefficients have units?
Um,
Is it percent per percent?
well, that would be unitless, right?
Not exactly.
Percent per percent, isn't that?
It could be
No, percent
probability of Democrats winning per percent of Democrats in that county.
Yeah, except that we're in the log territory, so it's not even that. Yeah. So you could, let's see here. Actually, I must have taken that out of my notes. Okay. So it's 48 and negative 23. Okay, so beta 0 is equal to negative 23. Beta 1 is equal to 48. Okay, so you could, so if I wanted to find out the probability of a particular outcome, right, the way that you would do it is like this, negative 23 plus 48x. And I actually, you'll notice that there is, unlike in a linear regression where you can say the beta is the slope and it changes, and any point on x, my slope remains the same. Well, that's not true here, right? If I go from here and I go 1 unit in the x direction, the amount that changes in the probability is like this. But if I'm here and I go 1 unit in the x direction, the amount that changes is like that, right? And so now you have this nonlinear relationship between the probability outcome and where you're starting on x. And so that matters as well. So we can't make this simple thing about, oh, as x changes by 1 unit, y will change by some amount. Now it depends on where you're starting in x, okay? So that's one piece that's also different. Okay, and so you can go in here, plug in an x, and then solve for the probability. And actually, if you were to do that, in this form, it will look something like this. Beta 0 plus beta 1x divided by, it's 1 minus that, right? So 1 minus beta 0 plus beta 1x. Yeah. So I can plug in my negative 23, my 48, and then my whatever value I want for x to calculate the probability of a particular outcome given those coefficients that we're solved for and an x as a starting point. Okay. Yes?
So if we're working with like a categorical response variable, can we just assume that like the coefficients we receive are kind of in that log odds form?
No, well, so we don't have to do transformations on the x's, only on the y's.
Okay.
Yeah, so the lesson here, right, is that the interpretation of coefficients is less than straightforward for logistic regressions. And I kind of unfortunately see, if you look at published papers that do logistic regressions, they'll show this table, and then they'll talk kind of qualitatively about what these coefficients mean, kind of like the way, Simon, you were talking about, which is if it's positive and it's larger, it has like a bigger effect on, blah, 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 right? And we do that because these coefficients, the numbers themselves, are like very difficult to interpret. But I would encourage you guys not to do that, or to actually do a little bit more, because there are ways that you can show what the relationship is between my or there are better ways that I can show the relationship between my x and my probability of outcome based on the model fit in better ways, right? And so the better way is to do it in probability space. So let me show how you might do that instead of just publishing your coefficients that no one can really understand what's going on. So I'm going to create a data frame that I'm going to be predicting on. And I can use the predict function to get the outcomes. And there are actually different options for predict when you're dealing with logistic regression, right? I can actually predict the zeros or ones, but I can also predict the probabilities associated with the zeros and ones, associated with each value of my percentage Democrats. And so if you run it just by default, I have to %dem not found. All right, one sec. Oh, X%. Oh, what the heck? Oh, oops. This should be an equals, not a comma. Okay, there we go. So now I've predicted over this sequence from 0 to 1. And where is that guy? Oh, I added it as a column here. So in the default, it's actually giving you the log odds ratio, which is not what we want, right? We want the probabilities. And so here, you can put in an option called type equals response. And this will instead of giving you the log odds ratio, it will give you the probability of the outcome, which looks something like this. Okay, and so if I put this into a plot, okay, run this guy. Okay, so here we can see right, as you change the proportion of registered Democrats, the probability that a Democratic candidate wins will look something like this, right? What do you guys think is easier to digest, this plot or those coefficients? The coefficients? Okay, well, I'm glad you're really good at doing log odds ratio math in your head, but for the rest of us mere mortals, I kind of much prefer this, right? So, yeah, working, I think, in the probability space is much more like intuitive, and I would actually really strongly recommend that you guys think about working in this space as opposed to log odds ratio when you display your results for like logistic regressions. Does anyone have any questions? Yeah.
So if you were going to describe that in a paper, would you like you'd say something along the lines of when you start to see that like, probability increase a lot? Like, how would you describe that?
Oh, yeah. I mean, I guess it depends on kind of what you're talking about. I would usually just be like, hey, you could look at the plot and probably understand pretty well kind of what's going on. It'll get a little bit more complicated. We're going to talk about like how to interpret this in multinomial logistic regression. And actually, there's one thing. There's actually two outcomes, right? So we have a binary set of results. One is which the Democrat won, and one in which the Democrat lost, right? And so this is showing when the Democrat candidate wins. what about how, what about that other result? What is that in relation to, what is the probability that someone loses, a Democrat loses, in reference to the proportion of registered Democrats?
1 minus this.
Correct, yeah. So this plot actually shows two results, which you could plot by just doing 1 minus. And so it would look like this, and then whoosh, right? So 1 minus that. And so that's really important to keep in mind. This is very much akin to, like, in the categorical and dummy variables, how we have one result that's kind of left out. And then you can infer what that is based on the information that you get from the results. And we're going to use that when we think about multinomial logistic, right? So if you have 3 outcomes as opposed to 2 outcomes, you will see 2 lines, right? And the third line you can generate by doing 1 minus each of the probabilities for your other 2 lines. Okay? Any questions? Okay, so let's continue onwards. Yeah.
Did you say again what your absence for?
Generalized linear model. Yeah. Okay. I'll go through this next part kind of quickly. This is just kind of for reference. So unlike an OLS, logistic regressions are solved. So if you want to figure out how we actually get the betas, it's actually different than with an OLS via maximizing
What is an OLS?
ordinary least squares. That's the linear regression, right? And so we talked about in a linear regression, we do the you can either get your betas by the analytical solution xtx inverse xty or gradient descent, right? For logistic regressions, that is not how we solve for the betas. We maximize the log likelihood function rather than minimizing the sum of squared errors. Okay? Yeah, and in this case, actually, this doesn't have an analytical solution, so this iterates through to figure out what the betas are. So this does it in a numeric optimization as opposed to a closed form solution. And the LL function, so what is the likelihood function? This describes the plausibility of a model parameter value given specific observed data. Okay, you guys don't have to memorize this, but it looks something like this. I don't even know why I show you guys this. Like, I've only worked with this in like statistics classes. I've done lots of logistic regressions, never had to think about this. But just reference in case, yeah.
Are they all natural logs, right?
Yeah, log is natural log, yeah. All logs in this class are ln, always. I think I already read this once, but
Oh, yeah. That's good to remember.
yeah, just to refresh, all natural logs. Yeah, we don't do base 10 up in here. Yeah, so you basically set partial derivatives dl d beta j equal to 0 and approximate numerically. Yeah, if you want to do lots of these fun theorems, you can take a real stats class.
Is that just like nudging around the betas until the likelihood stops changing?
Kind of, but in a much smarter way, right? Because when you set the derivatives, right, you are, you're trying to replicate kind of what you would do analytically. Yeah. Okay. Cool. And I already talked about how the lines will always add up to 1. Okay, and so let's move on to the next step, right? Which is multinomial logistic. Okay, hang on. Let's actually take a break for a second. This is a good spot to take a breather. So let's do like 4 minutes. Yeah.
So, in the first example,
Uh-huh.
when we were playing with election data,
Yep.
you mentioned that it's logged, right? You mentioned that this plot is logged.
Oh, no. I was saying if you don't include type equals response, the prediction outcome that it gives you is going to be the logs odds ratio. So if you delete type equals response, you'll see that it gives you something different.
Yeah.
Yeah. So if you look at the data, you get these values. And these values correspond to so that is this thing. Yeah. And when you do predict, you can get this thing, or you can actually just ask it to give you this thing.
And that's by doing
Type equals response. Yeah, exactly. Make sense?
Yes. I was like wondering what the log thing can.
Yeah.
Thank you.
Yep.
Hello.
Hi.
So I'm struggling a bit on homework.
Okay.
In a couple places, but
Okay.
but first, when you're asking for, what is the correct MSE for the correct versus incorrect mouse points?
Yeah. People are getting this question a lot. So
Okay.
you basically want to run your model calculating mean squared error for a subset of data, and
Okay.
the subset being the ones that are clean, and then you get an MSE, right?
Yes.
And then you can also run them against the data that's dirty, and then you would also have a different MSE.
So by that, do you mean having those two in completely separate?
Predictions.
Okay.
Yeah.
And how would I format that? I'm just having some difficulties kind of understanding the code and how I can personally apply it.
Yeah. So the idea here is like really understanding where it comes from, right? And so let's say you have a model that you've calculated and is correct. Y equals beta 0 plus plus beta 1x. And then you have a data set D where you have like some set that's correct and then a subset that's incorrect, right? So how do we calculate an MSE?
Right. It's
So it's y minus y hat
yeah, the hat.
squared, right? So I, and then divided by n, right?
Yes.
Yes.
Yeah, and that's partly where I'm struggling because I've been looking online for help, and it seems like there's a lot of talk about like predicted versus observed and whatnot. But
Yeah,
that's-
this is your observed and this
Yeah.
is predicted. So let's say this is my y and my x's. So let's say A, B, C, D, and then maybe I'll have E, F, G here, and then here. I'll just do 1, 2, 3, 4, 5, 6, 7. So what I would do here is I would do my observed value, A minus, so A minus beta 0 plus beta 1 times 1, right? And then I would do this plus,
everything else.
yeah, so B minus beta 0 plus beta 1, 2, right? And I would do that up until here.
Right.
And then I would add them up and divide by 4.
Right.
And that would give me the MSE for the correct values. And then for the incorrect values, I would just repeat this, but I would do it E minus beta 0 plus beta 1 times 5 plus F minus beta 0 plus beta 1 times 6 plus, and then that would then give me the MSE for
Right.
this.
Okay.
Does that make sense?
Yes, that makes sense.
Yeah.
Just to make sure, in terms of getting the beta 0 and beta 1, would that be found in our summary, in our previous steps?
Yeah, exactly. So whatever model that you used that you arrived at, you should use
Yeah,
that
the
model.
new one, right?
Yeah, you should use that model to calculate these guys.
Okay, great.
Yeah.
Awesome. Thank you.
Yeah. Okay. And back to here. So multinomial logistic regression, this is just a generalization of logistic regression to multi-class problems. And so we were first dealing with a binary outcome. So you have f of ki, where this is our outcome, and this is our observation. Then you have something like beta 0, comma k, plus beta 1, comma k, x1, I. Right, and so we were looking at percent Democrat, and then Democrat win. 1, 0, 1, 0. So here, K has only 2 outcomes. Okay? Straightforward so far? And the idea is now we want to extend this to thinking about multiple outcomes. So FKI becomes, so same thing, K plus beta 1, comma K, X1, I. So this is equal to a vector of betas for every different outcome. So this is a little bit different, right? So this actually means that for any outcome in your response variable, you actually have a different set of betas describing the model fit, okay? So now k can be greater than 2, and you have a different set of betas for each outcome. Okay? So we used to have something like this, probability. So this would be probability for y equals 1, and then I would have something like this, probability for y equals 0. And now I might have something slightly different, where maybe I have something like this. Probability y equals 1. Maybe I have something like this. Oh. Where probability y equals 2. And then I might have like a third line, probability y equals 3. And I can calculate that line by doing 1 minus the sum of the blue and red probabilities, right? This probably doesn't look quite right. It should probably be, given the way that I drew it, it would probably look more like that. It should go down. But hopefully you guys get the gist, yeah.
So this is not a case that we have still just one basically input variable, or still just the Democrats, like the
Yeah, in this case.
Then you have 3 different nodes. Maybe if for example, you have 3 parties or something like that, right?
Yeah, okay. And so how would you visualize and deal with, in this case, right, you only have one explanatory variable, and so the question might be, how might you visualize in probability space multiple variables? It starts to get complicated again. Oftentimes what you can do is, we'll look at an example where we can do it in at least 3D space if you have 2, but then the common way people deal with this is you might hold one variable fixed and then look at the variation in probabilities across a range of other variables. So that's a common way to do it. Yeah. Yes, it's maybe a little bit limiting, right? But it's still better than trying to interpret log odds.
Or you can figure out the visualize in 4D.
Yeah, I mean, it's possible. It does get more complicated the more dimensions you add. 4D, you could do it with like colors and gradients. Yeah, and then in like more dimensions, you could add different like color scales, but it does get it gets pretty counterintuitive at some point to do something like that. And usually, you know, so what I'll say, so going back to our discussion of like the causal world, inference world versus predictive world. Well, in the predictive world, you don't really care about this visualization, right? You just care that you're getting as accurate as possible outcomes, which I think we're gonna talk about. Yeah. Actually, let me talk about that in just a moment. yeah, so in predictive world, we care just about the outcomes. You don't necessarily, again, care about the relationship between the outcomes. And then in the inference world, probably there's only like specific things that you really want to understand the relationship with, and most of the other things in the model are acting as controls. So then, in that case, the ability to do the visualization focused on one or two specific explanatory variables means that, yeah, you could still do this kind of thing, holding your controls constant. Yeah.
Can you still calculate like R squared and C and all these things?
No, yeah, the metrics are a little bit different. So we have something called like rho squared that's similar but different. Yeah, but you can always do MSEs. So well,
Okay, can you?
yes, but it's a slightly different interpretation. Yeah. So. What are the observed outcomes for this? Ones and zeros, right? But we might be dealing in probability space. So how do I get from probabilities to the ones and zeros? Well, you can, like I was saying, once you're above 50%, just make a rule that it assigns to one outcome, and below 50%, it assigns to your other outcome. But there's actually some interesting things to think about here. I can okay, let me do it over here. You can predict correctly. So let me see. Let's say this is, let's say our binaries are, or I'll just write it like this. Okay, 1, 0, 1, 0. If I make a prediction and I got the right outcome, right, you could do this. You could make the wrong prediction for a particular sort of observation. And this is some kind of error. You have a different type of error here. And then this one is, sorry, this one would be a check mark, right? This would be correct. Okay. Why does this matter? Let's say you have a model to predict whether or not someone has an extremely, or actually, let's not even do that. Let's say you have a model to predict whether someone has cancer. Okay, so if they have cancer and you've predicted that they have cancer, good, right? You can send them off to treatment. If you predict that they have cancer, or that they don't have cancer, and they also don't have cancer, you're fine. You could predict that they don't have cancer, but they do have cancer. And you can also predict that they have cancer, but they don't actually have cancer, right? So this is known as type 1 and type 2 errors. False positive and false negative. So this would be a false positive, and this would be a false negative. So false positive, false negative. I always forget which one is type 1, which one's type 2. Does anyone know off the top of their head? Okay, you can look it up. Which one's worse? If you,
Depends on the situation.
yeah, well, so, yes, okay. It does kind of, maybe this is a little sensitive, but, right. Okay, I'll say if it were me, I would much rather hear that I got cancer and not have it, right? Because then in that case, I could be like proactive about it, see more doctors, figure out that like I actually don't have cancer, compared to them telling me, oh, you don't have cancer, and then I'm like, okay, I'm good, but I actually have cancer, and then I don't treat it, right? So in some cases, in certain types of problems, we care a lot more about getting this stuff right versus the other ones, so false negatives versus false positives. So you can calculate a mean squared error, right, which is how often you're getting things wrong versus how often you're getting things right. And you could do the same type of things that we've been talking about. You could do model selection, you could do regularization to calibrate your model. But actually there's something interesting here. Rather than caring just about the sum of these errors and minimizing that, in some models you might actually prefer to minimize a poor outcome that's associated with a false positive or a false negative. And in which case, you might actually choose a model that has higher errors in totality, but has lower false negatives or lower false positives. Okay, so you should think carefully about the calibration of your model as it pertains to errors in these discrete models, because sometimes you actually care a lot more about reducing certain outcomes rather than the total errors. Does that make sense? Yeah, and so roughly speaking, if we're talking about in kind of the parlance that we have about like subset selection, right, where I have, let's say, variables x1 through x4, and let's say variables x1 and x2, if I do all the stuff that we've been doing and I reduce my total errors as much as possible, that may have, let's say, a total error rate of like 20%, right? But it may have a false negative rate of 15% and a false positive rate of like 5%, something like that. I might actually choose a model that's like x1, x3, right, that has a total error of 25%, but it may only have like a 10% error here and a 15% error there. So even though the error is bigger, I'm calibrating the model differently and preferring to reduce a subset of the errors as opposed to the total of all the errors. Does that make sense to everyone? Okay. Any questions? Yeah.
How do you know what type of error that we're getting from RLCs?
Yeah, so when we do the prediction for those probabilities and you assign values based on the probabilities of zeros and ones, right? Your observed might be 1. It'll look like this, right? Your observed will be 1 and your prediction's 1, that's fine. Your observed might be 0 and your prediction is 1, in which case you got a false positive.
We just count how many?
Yep, and you just count it up. Yeah. Okay. That's weird. One second. Um, okay, so this part you guys don't need to follow along with. There's a bunch of code here. For some reason, I have it like replicated twice, so I'm trying to figure out why. Okay, so that's fine. So yeah, this is all going to be yeah, online as reference. So don't feel like you need to totally follow along. And I probably need to load in a couple of. Okay, so I have some data called Disney. Okay, and so this is a data set that looks at TV shows and movies on the Disney network. And it tells me some information about like the year, what I'm gonna call the certificate, which is the movie rating, like if it's R, PG-13, and then for TV shows, if it's like mature or whatever the other ones are, TV-14, okay. It tells you how long the movie is, and then the reason why I call it a certificate is we also have ratings. These are just like people vote on how good the movie is out of 10. Yes, so this is like a very arbitrarily constructed regression, but the idea is I want to know what the relationship is between the certificate or the movie rating. So we're only going to look at movies, and how long the movie is, and the rating score of the movie. And I've done a little bit of filtering. So I'm only looking at movies. I'm only looking at things that are less than like 3.5-ish hours, and they all have to have a rating above 3. Just makes it a little bit cleaner. Okay? So this is like a 3D plot, right? So we have outcome. So our outcome, there's 4 possible outcomes, which are the 4 different certificates: G, PG, PG-13, and R. And then we want to look at how they're distributed via the movie runtime and the rating of the movie. Okay? Yes?
What is a movie or 0 minutes runtime? Is it a picture?
Might be interpreting out of it.
Oh yeah.
You know?
Yeah.
Oh, yeah.
You know, I wasn't being super careful with the filtering. This is probably something that it just didn't have an assigned length, so it's probably just default 0. We should probably kick those out, but whatever. It's only like 5 points or 10 points. No, 7 points. It's fine. Yeah. Okay, so I can run the multinomial logistic regression, and I can look at a summary of it, and we'll see a whole bunch of stuff here. Okay, what are we looking at here? So we have coefficients and we have standard errors. And so for the outcome of PG, it has an intercept value of negative 0.14, runtime of 0.01, and a rating of negative 0.08. Okay, and so if I were a lazy modeler and I put this into a paper and I would be like, well, as the runtime increases, the probability that these things happen, so PG, PG-13, and R, the probability that it's one of those increases as the movie increases in length, with the most likely being PG-13, right? Because it's the largest in magnitude relative to these guys, right? And then as the rating goes up, it's less likely to be a PG movie, and it's more likely to be a PG-13 or an R movie, and it's more likely PG-13 than R as it goes up, and that's all in reference to what? How many certificates are there? 4, right? So we've left out G. You can actually calculate the values and probabilities associated with G, right? Because in the same way, we have to leave one out in the same way that we do with the dummy and categorical variables. Yeah.
Up a little bit, see the weight thingy. What is that about? Where's output the model with some given summary in the console?
Wait, in the console?
Yeah.
Oh, this thing here. That is 4 times. Shouldn't it be 12? It's the where's my intercept. Yes. It's the number of parameters, right? So you have 9, no, it should be 12.
When you run through the interpretation of these coefficients numbers,
Yeah, 1 second. Okay, I'm probably misinterpreting what the weights are then. I'm actually not sure. I will get back to you on that. Yeah, interpretation of the coefficients, these are all just like log odds ratios. I don't know how to really interpret these other than to say, if it's positive, it means the probability increases as these values increase. If it's negative, the probability goes down. And then the magnitude and size of it means that, it's more likely relative to the other ones.
okay.
Yeah. But yeah, this table is not as useful to me. But if we go to our probability space, we can actually do something like this. Oh no, are these not scaled? I think I made a mistake. Oh no, it's actually, this is fine for, yeah, you don't need to scale on this one. Okay. So this is like a slightly different way of visualizing in this space. Do I actually generate the plots? Yeah. Okay, so if you run the model and then you predict outcomes from the model at every sort of given combination of values between movie runtime and voted rating. So if I pick a point here, right, it will generate probabilities for all of my possible outcomes, and the one that it actually predicts, or the one with the highest probability will be the one that I choose to represent as my prediction, and you can see what that looks like over this space here. Yes, and so in this space, when I go up to a movie runtime of, I don't know, 30 minutes or whatever that is, and then as the vote rating changes, I would predict that it has a G rating. Over here, I would predict that it has a PG rating, and over here, I would predict that it has a PG-13 rating. Yeah.
And this, I did this by the expand grid.
Yes. Yeah. You can look in the code to see how we do it. Yeah. And so, what else is kind of interesting about this that you guys notice? Yeah.
Tends to dramatically miscategorize G-rated movies.
Well, so one of the features, I don't really talk about how this comes about, is that the decision borders for my choices are linear in a logistic regression. Okay, so actually, you're saying that it does a really bad job, but actually, this configuration of predictions of red, blue, green, any other way that I would draw the line would actually result in more errors. Yeah.
The one thing I would maybe include is that you also have like maybe a darker red, the more it goes to 1% probability, and the lighter.
Yeah.
color.
You could do that. Yeah.
Keep the RGB right here, that's a color.
Yes. But you'll also notice there's 4 possible outcomes, but this is only predicting 3 of them. So in this particular case, in this particular example, it just so happens that the purple line is always lower than the other 3. Yeah.
According to the model, are like the outcomes exclusive?
Well, they're probabilistic, so at no point is the probability of any outcome 0, most likely, and so they're not mutually exclusive, right? There's always some chance that an outcome could happen, but it might be lower or higher depending on where you are. And let me see if I actually have.
I get that. It's just like, I mean, in this case, they are exclusive. We know they can't do both G and PG, but sometimes more classes can also be sometimes
So, in any discrete choice model, right, there's one outcome that happens. So you could call it mutually exclusive, right? Like the fact that a Democrat won, right, and a Republican lost, it's either that or the other, right? But the idea is that if you repeated the experiment many times, there's, right, some probability that you might get a different outcome, right? And that's what this is kind of indicating. This is uncertainty in a particular outcome. Okay, so if you were to graph the probabilities, you do the prediction kind of as I was saying before, you would actually see something like this. So this one holds the movie runtime to the average, and then it plots the probabilities across the range of ratings of a particular outcome, right? And on the sort of average one, at the average runtime, which might probably be kind of in the middle here, right? If the average runtime is like right here, then across all of my ratings, the blue is the most dominant, right? Up until right at the top where the green takes over, which we can see. We can see happening right over here, right? So this set of probability curves is akin to the probabilities across a range of a fixed runtime. I can also do the same thing holding this fixed and looking across that way, and that would look like this. And so this is the movie rating getting held fixed across a range of runtimes. The scale is transformed, but this is the full range. And you can see we start with red at low runtimes, we go to blue at longer runtimes, and then at the longest runtimes we have green, right? And so that is kind of exactly as we see over here, right? Red, then green, then blue, then green. And at no time do we ever see purple being on top, so the model never thinks to choose R rating as the most likely outcome. Okay? Yeah.
Is it possible to graph top 2 or 3 in the grid method, or do we always have to pull out a second graph like this to see how the probability changes across?
Yeah, I mean, I'm sure you could come up with some creative visualizations here. Yeah, there's different ways to do it. You could have you could try and represent this in a mix of colors to some degree. Maybe it'll be harder with 4 outcomes, right? But you could shade it based off of probabilities. Yeah, it gets a little tricky, but yeah, you guys are creative. You can think of something. Okay. Any other questions about multinomial? All right, let's see here. So logistic regression is not the only way to do these discrete models. And so other examples of classification. Let's talk about these. So one is known as linear discriminant analysis. I'm trying to figure out how to balance with the remaining time here. Okay, so what I'll say is, what I'm going to do is we're going to skip the theory of LDAs. You can check that in the notes. What I'll kind of point out is that an LDA is pretty similar to a logistic regression, but let's talk about some of the differences, and then I'll just quickly blaze through some results, and then we'll talk about a more interesting one. So this is better for well-separated classes. if predictors are normally distributed, it is more stable than logistic. And this is popular with more than 2 response classes. So when it comes to deciding whether you want to do an LDA or a logistic, these are some of the things that you might think about. Yeah, we're not really going to talk too much about LDA. I feel like I kind of mention LDA as something to add into your tool belt. And so, again, this code will be available for you guys online later. Doing the exact same thing, but using an LDA model, you end up getting results that look pretty similar. Yeah, so in this case, you also have linear boundaries with an LDA, and these may look just slightly different from a logistic regression. And the effect may be more or less pronounced or more different than a logistic depending on the context of the problem. But this is another common model that people employ when they're doing these discrete choice models. Okay, but let's talk about a more interesting one. This is, yeah, kind of just for reference for you guys. Yeah, the one that I think is more important to know about is known as K nearest neighbor. So probability y equals j, x equals x0 equals 1 over k sum this is the math behind K nearest neighbor. I actually, well, okay, I guess I kind of know what it means, but when I first looked at this, it was like total mumbo jumbo, and I don't think you guys should think about this at all. Actually, K nearest neighbor is a fairly simple concept to grasp. So let me describe it, and I think you guys will have a much better understanding. So given a positive integer k and test observation x0, identify the k points closest to x0, represented by NO. Estimates probability for class J as the fraction of points in NO whose response equals J. Classifies XO to class with largest probability. Okay, what the heck does that mean? All right, we got our X's and O's here. Famed rivals. All right. Let me put is question mark a X or an O at K equals 1, K equals 2, K equals 3. All right. K equals 1. Who is the nearest neighbor to this question mark? This guy. Distance-wise, right? So at K equals 1, this question mark is it an X or a no? It's an O. It's a blue O. Okay. At X equals 2, let's say my closest neighbors are here and here. So I'm now tied. And in a tie, I'll go back to the last one. So this is an O still. Okay. What are my 3 nearest neighbors? Maybe here, here, and we'll say this one. So that means this is an O. My 4 nearest neighbors, here, 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 tied, so still an O. Okay, 3 nearest neighbor, or 5 nearest neighbors, here, 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 now it's an X, right? You get it? Pretty simple, right? So basically, you look at my 1 nearest neighbor, 2 nearest neighbor, 3 nearest neighbor. What about, what if K is equal to 50? What would this be, an X or a no?
Oh.
1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there's more O's than there are X's, which means the larger I go to K, the closer I will converge to whatever one's the biggest, right? Okay, so I'm right here, okay, and let's say K equals 5, it's red X. K equals 10, still red X, but K equals, how many was it, 20? What would it be? It would be an O, and it would be an O anywhere in here. How do I choose K?
Some fraction of how many points you have?
No. What do I fundamentally want from this model? To give me, not probability, I want the best possible prediction. And to get the best prediction, I have to do cross-validation.
Cross-validation.
Right? Yeah, anytime, remember the answer is always cross-validation. Right, so if I want to choose the correct value of K, I want to make it so that when I'm actually putting points down, that my prediction matches, let's say, like a test set or something like that, right? And so the way we do that, cross-validation, without a sample stuff, get my best K that gives me the best prediction outcomes, okay? If K is too small, I will overfit to things that are close to me. And if K is too big, then I will have bias. Yeah, my bias will be too large. Okay, so let's jump back over. Okay, so actually before I even start all of this, for k nearest neighbors, I run through some stuff here where I call Disney.normalized. And I'm scaling my runtime and my rating before I do any processing. And so why is that?
Just go from 0 to 1.
Yeah, I'm gonna scale everything to be, yeah, basically 0 to 1. Or at least in the same scale. And why is that? Let's see. Let me pick. Okay. I'm going to. Okay. I'm going to pick this point right here in k nearest neighbors. Do you guys think at k equals 1, is that blue or is that red? Red? Yeah, so if I did not scale this, wait, am I, no. I'm trying to do, oh no, I want them this way, sorry. If I'm, okay. Yeah, if I'm like, right, wait, I'm trying to do this example. Well, all right, basically, I have a brain fog right now. Okay, so.
Force it to graph like square. That way it'll make the pointing easier.
Yeah, well, it's about this distance versus this distance, right? These distances are like a lot bigger than these distances. And that's just an artifact of the way that the variables are scaled. And so if you're doing k nearest neighbors, don't make a mistake of just putting these values in, because that stuff is going to totally override this variation, right? Because these are so close together in just the range of the values compared to these. And so, yeah, you can really think of this would actually be like super compressed, right? Because of that. And so I have to normalize the values. Which I actually did this example for a couple years, and I didn't scale the values for like 2 or 3 years, and no one noticed. Actually, someone noticed, and then I fixed it at some point. Let me. Okay, so in k nearest neighbors, there's no reason why the boundaries need to be linear or anything, right? And so it ends up looking something like this. What K did we choose here? Oh, actually, this is, so if you'll see in the code, this one uses an automated version of picking K such that I have the lowest error possible. So this is kind of like the best K. And so you see, looks something like this, right? And so at whatever K value this is, if I pick a point here, it's going to look at the nearest number of some number of neighbors, and then predict that it's blue, right? Because that many people close to this is blue, and you can see kind of the boundaries are kind of all over the place. But yeah, so looks pretty different with KNN. Yeah.
Can you actually call K nearest neighbors a regression? Like,
Yes.
Is it actually like
Yes.
predicting these values, or just
It is predicting.
observing the data set when you ask it to?
There's no data here, but it's making a prediction.
Well, it doesn't have to make a prediction, it just looks at the, in some radius around it, or like some number of neighbors within it.
Yeah.
Oh, that's blue, so it's just looking at the actual data rather than trying to
It's looking at data to make an informed outcome,
Yeah.
make an informed prediction, right? So it's right. Definition of regression is is a model that describes the relationships between inputs and outputs, and so that's what it's doing. It's looking at the data, but maybe in like a different way, right? And it's still giving us an output. Yeah, and so this is KNN, example of classification. And I have one last thing where I can actually instead of choosing the optimal one, I can look across a different range of Ks and see how the predictions change. There's a bunch of these, so it takes slightly longer. But yeah, so one other thing I wanted to mention is that with KNN, you don't have like a beta coefficient or anything like that, right? So KNN really is more on the like prediction world of models as opposed to the inference type of models, because you really can't make any inferences about the relationships. It's all super non-parametric. It's contextual to exactly what you're pointing out in the data. And so that's actually one of the reasons why things like logistic models still tend to be used, is because we can still describe relationships between inputs and our outputs, as opposed to KNN, which will, I think, almost always give you better predictive outputs than your logistic, but will tell you nothing about relationships between your inputs and outputs. And why is this, is it still going? Come on. Well, while we wait for that, I'll just show you. At k equals 1, it looks something like this. K equals 2, 3, yeah. So it's messy, and these will converge to the plot that you saw before.
Eventually it will just convert to one color, right? The one that was like
Yeah, eventually it will converge to one color.
But you have a massive error.
Yeah.
Sure.
So like here, my nearest neighbor for 1 is red, right? Over here, the closest one is blue, so yeah. And then with 2, the overlaps, the 2 colors means that there's a tie. Yeah, so it is quite messy, right? But then this will eventually get to the K that we chose in that earlier plot, and then eventually when it gets really big, it'll just go to one color, which I think is blue, because there are the most dots in the plot are blue. So, yep, that's it. Can end. Sorry for keeping you guys over time a little bit.